Here a conducting wire of parabolic shape is moving with the velocity v naught I, and equation of parabola is y equal to x square. Then the magnetic field is b naught in bracket 1 plus y by l raised to beta. It means it is continuously varying along the y. It is along x, it is constant, but it is varying along y given by this relation. Then delta phi is a potential difference developed between the ends of the wire. So this information is provided by the problem setter, and then we have to check the correct options. First of all, what they are saying is delta phi in this at beta and delta phi at beta. So it means I need to find a generalized expression for delta phi. Now if you see carefully and if you take some small elemental part of this, then it will have two components. One will be along this, one will be along this. So along this will not have any effect in the induced EMF. So only this dy part of the small elemental length dl will be responsible for the induced EMF in it. So if I want to check what is the induced EMF in this much small part, that will be BLV. So DE is going to be the B at a distance of y is B naught 1 plus y by L raised to beta. Then L is nothing but dy and the velocity is nothing but v naught. So this is actually a very small induced EMF in this very small elemental part dl. Remember that its x part is not going to induce any EMF because it is having a velocity in this direction and the length vector will also be in this direction. Here dy is perpendicular to velocity and perpendicular to the magnetic field, and in such cases the EMF induced is BLV, and hence this is the induced EMF in a very small part. So to find the induced EMF in the complete part, I'll have to integrate it. What will be this integration? This is going to be E, and that integration, so it is going from y I will have to integrate, so 0 to L. So if I solve this, it is going to be B naught V naught. This will be integration of dy 0 to L plus integration of y by L raised to beta dy 0 to L. Now how much will be this? This is B naught V naught in bracket L plus, this will be y raised to beta plus 1, y raised to beta plus 1 upon L, and this will be beta plus 1, where it is ranging from 0 to L. So if I solve this further, I'll get this as B naught V naught L, this will be L raised to beta plus 1 upon L, here it is L raised to beta, so it will be L upon beta plus 1. So this is going to be how much? B naught V naught L 1 plus 1 by beta plus 1. This is the most general expression of the EMF induced over the complete wire. Now here if I go for the first option, when beta equal to 2, this will be 1 by 3. 1 by 3 means this will be 4 by 3. So answer will be 4 by 3 B naught V naught L, and hence the answer option A is the correct answer. If I go for beta equal to 0, just substitute here, so it will be 1 plus 1 2, so 2 B naught V naught L, but it is given as half B naught V naught L, so this is incorrect answer. Then the fourth option, if you see, it is given as delta phi is proportional to L, that is the length of wire projected on the y-axis, and it turns out to be the correct because E is proportional to L, and L is what? It is the projection of this along y, because only the y part, only the projection along this vertical direction is responsible for the EMF induced, and hence this answer is also a correct answer. Now the next question says that if the parabolic wire is replaced by a wire with y equal to x, means everything is as it is, only what you are doing, instead of y equal to x, it is y equal to x square, it is y equal to x, and its length is root 2L. Now if you say that its length is root 2L, naturally this will be L, this will be L. So its vertical component will have a length L again. Now again the similar story repeats, that if I go for small elemental part and if I take dx and dy, then only dy will be responsible for the EMF induced, and the integrations even in this equations are going to be same, because it will be in the same manner I'll have to integrate, and it will be 0 to L, so it has to be same, and hence this answer is also the correct answer. So the answer options for these questions are A, B and D. Here, a perfectly conducting wire is moving with the constant speed of 1 centimeter per second. Its length is 10 centimeter. Here there are two components, one is inductor, another is resistor. So having a inductance of 1 millihenry and resistance of 1 ohm. E raised to minus 1 is 0.37 is given. Magnetic field is 1 Tesla, which is going inside the board. And what we have to find is the current in this at t equal to 1 millisecond. So first of all, I'll have to write the equation that how the current varies in the inductive circuit. Now, well, it is going to be I equal to I naught 1 minus e raised to power minus t by tau. Now this will be equal to I naught 1 minus e raised to power minus. Now t is 1 millisecond and tau is L by R. This is 1 millihenry. This is given as 1 millihenry and R is 1 ohm. So because all the values are 1, this I will be equal to I naught 1 minus e raised to minus 1. E raised to minus 1 is 0.37. So it turns out to be 0.63 times I naught. So now your job is to find this I naught, because once you get this I naught, you have the answer. Now how you will get the I naught? I naught is the maximum current flowing through the circuit. Now whenever even after a large time, when this circuit is going to achieve a steady state condition, your I maximum will be equal to BLV by R, because at that time your inductor will start behaving like a short circuit. Remember that capacitor, when you close the switch, behaves like a short circuit, but after steady state it behaves like an open circuit, whereas inductor, when you are closing the switch, behaves like an open circuit, but after a long time, after a steady state is achieved, it behaves like a short circuit. So here the maximum current is going to be BLV by R, which is going to be magnetic field is 1, your length is 10 into 10 raised to minus 2, your velocity is 10 raised to minus 2, and resistance which we have is 1. So it is going to be 10 raised to minus 3, which is I max. Therefore, how much will be the current at t equal to 1 millisecond? It is going to be 0.63 into 10 raised to minus 3. So naturally, if I compare this with this, then x turns out to be 0.63.